So hello, I will present my master thesis, which is the machine learning for probabilistic robotics with Webots. My name is John Sebastian Gerard Salinas, and my promoter is Gianluca Bontempi. I work with ULB together with the machine learning group. This presentation is oriented to give you an idea of what you can do with machine learnings in robotics using a simulator called Webots. So I will go for an introduction, then I will talk a little bit about probabilistic robotics, then how you can use machine learning in probabilistic robotics, and finally I will give you a demo. So a mobile robot is a vehicle that moves autonomously through navigation. And navigation is about controlling and operating the course of a robot. So to be successful in navigation, you need to be successful in 4 other blocks, which is sensing, when the robot perceives the environment using the sensors, localization, where the robot localizes itself in the environment using sensory information, cognition, where the robot, once it's localized, creates an execution plan to accomplish a certain goal. And finally, control action, where the robot executes the execution plan by modulating its output motors. And to be clear, each one of these 4 blocks has its own research area. And this work is focused on the localization part. So local versus global localization. For the local localization, the robot knows its initial position in the environment, and the objective is to track the robot's position while moving. In global localization, the robot does not know where it was initially positioned in the environment, and it has to discover while moving. So addressing global localization is more difficult than local localization. Why is it difficult for a mobile robot to self-localize? Well, there is no direct mapping from sensor measurements to a position in the environment. Then you can say, okay, let's just use a GPS or a bunch of GPSs. But the problem with GPS is that it does not offer the required precision, especially when the robot is an indoor environment. And also the robot has to deal with uncertainty most of the time. Deterministic approach to localize the robot requires extra feature in the environment, such as landmarks, which is impractical. In order to deal with uncertainty and seeking to provide a reliable solution, probabilistic robotics is used for localization, which is a bunch of probability theory techniques applied to robotics. The motivation is that there are many applications nowadays that can use localization for mobile robots, such as Mammoth, which offers mobile robots that automates data collection for farmers. Six River Systems and Locus Robotics supply mobile robots for the warehousing and order fulfillment business. And big companies such as Alphabet, Amazon, FedEx, and UPS are working on mobile robots for local packaging deliveries. A prediction made by Ash Sharma, who is the research director at Interact Analysis, says that Amazon will be using 120,000 robots by the end of this year. And the global market for mobile robots will surpass $3 billion, which is quite impressive. So talking about probabilistic robotics, there are many algorithms that you can use for probabilistic robotics. One of them is the Monte Carlo localization, where the robot is placed somewhere in the environment and the robot needs to localize itself. It does not know its initial position, so we are under the global localization problem. The only available information that the robot has is sensory information. In this case, we can put 4 sensors that measure the distance between the robot and the closest object, such as wall or furniture. A set of particles are uniformly distributed in the environment. A particle is basically a virtual robot. It does not physically exist. And it has associated a state to it, such as the XY coordinate and a rotation angle. And the robot also has a state. The difference between the particles and the robot is that the particles has also a weight associated with it. A weight represents how close the particle's state is to the robot state. So for illustrating purposes, we can see that the smaller the particle here means that the smaller the weight, which also means that this particle state, for instance, is very far away from the real robot state. Whereas these big particles here has a bigger weight that represents that their state is really close to the real robot state. The second part of the algorithm is called resampling, where the particles are randomly chosen with a probability according to their weight. So the particles whose weight is small have less chance to be selected for the next iteration. Then the algorithm goes on until all the particles converge through the real robot state, which can be considered as addressing the global localization problem, and we discover where the robot truly is using the particles state. So how can we use machine learning? So the difficult part of this algorithm is how to calculate the particle's weight. So in order to calculate the particle's weight, the theoretical way can be, for example, the robot can have integrated sensors to measure the distance between the robot and the closest wall. And for each particle, the particle has the power also to measure the distance between the particle and the closest wall. Then to assign a weight for this particle, for each sensor measurement, what the particles is perceiving also is compared to what the robot is perceiving. And then a weight based on the difference of these values are assigned to each particle. But the problem with this is that particles, they don't have sensors. And also the sensors that we are using here to measure the distance between the robot and the closest wall are simulated only, and they do not exist in real life. So what we can do instead is that using, for example, laser sensors, we can measure the distance between the robot and the closest object. And with machine learning, we can predict what the particles are perceiving, even though they do not have physical sensors with them. And then these quantities can be compared, and a weight can be finally assigned to the particle. So the process of doing this is that first we create a virtual world in a simulator using Webots. We can create a custom robot as well. Then we need to collect data in this environment. Basically, we make the robot walk randomly through the arena while collecting information about the coordinate and the rotation angle, together with the 8 sensor measurements, which are the 8 sensors placed around the robot. In this case, the yellow circles here are the sensors. And then we train models. In this case, we use neural networks. We train 8 neural networks each one of these is or receives x, y, theta coordinate, and it returns a sensor measurement prediction for every sensor. Then all this information is used together with odometry data to have a set of particles. Then once we have the set of particles, the weighted average is calculated to make a final prediction, and the result is visualized using a robot window, which is a tool, a plugin of Webots that can be useful to visualize the particles prediction. So these are the references that I used, and I will proceed with the demo. We have here the simulator, and here it's the visualization tool, the plugin that I created. And you can see that here is the robot. It is a custom made robot, which has integrated 8 laser sensors, which measure the distance between the robot and the closest wall, which are just the red points here that you can see. And the robot walks randomly, and the objective is, for instance, to predict where the robot initially is. So this is the global localization problem, and for this, a set of particles are uniformly distributed through all the environment. Each particle has a state associated with it, with x, y coordinates, and a rotation angle. So once you start the algorithm, you can see how the particles start. The particles whose weight is far away from the real robot state just disappear, and the particles in this case are handling, for instance, 3 major hypotheses, where they predict that the robot can be here, can be here, can be here, or can be here, for instance. So as the algorithm passes by, you will see that the particles will start converging through the real robot state, which is this point here. This point here. So the robot started here and it followed this path, and it's here. So this is a top view map of where the robot is. At this point, you can see that the particles converge through the real robot state, which is here. So in this case, we're going to try to address the localization problem. As you can see, the particles were initialized close to the robot state, since the robot knows its initial position, and the task will be that the particles will keep track of the robot positioning. The particles are represented by the orange points. The prediction made by the particles is represented by the red point. The real position, or the robot position, is the blue line, and odometry data, which is an estimate of where the robot is represented by the green line. So as the algorithm keeps going, you can have the option to disable the random movement and make that control the robot manually to make him keep going, or turn right, or turn left, or go backwards, forwards, and also you can modify some parameters of the algorithm, such as the number of particles, and and the standard deviation for the positioning and rotation. Like for example, you can give a really small number if you want the particles to explore more. You can add the number of particles, or you can just make them smaller. Like in this case, particles are going to start doing bad predictions, since this algorithm needs a bigger number of particles. So you can see that when you are playing with the algorithm, with the algorithm parameters, you can see that the prediction of the particles that are making now is really close to the real robot state, which is you can just see here, for example, that the last prediction made by the particles were here, and the robot is really here. So this algorithm is highly dependent of the parameters that you're using here. And that concludes our demonstration. I hope you like it, and thank you.